Good morning. So let us continue the lesson. I want to actually speed up a little bit the pace that we are doing things. So because otherwise we will not be able to finish a considerable amount of things. Okay, so I will continue today by the definition of the perpendicular bisector. So what is a perpendicular bisector? If you have a line segment, yes, any line segment, say AB, if you find the middle, exactly the midpoint, and call it M, so that AM is equal to MB, and then if you draw a line that passes through M and is perpendicular to AB, is called the perpendicular bisector, yes? So I draw this line that passes through M and is perpendicular to the line. And this is a line, so it continues forever from both sides, and that is called the perpendicular Yes, so that's the name for this. So every line segment has a perpendicular bisector. If I just draw a line, I cannot ask you to draw a perpendicular bisector because there is no midpoint associated with it, with a line. Yes. Okay. And now the point is that we want to actually talk about the theorem here. So what is the property of the perpendicular bisector? I think it seems trivial, but it is important to have it in mind, especially for the problems that you are going to solve. If I choose any point, say n, on the perpendicular bisector, the distance from that point to the A and B are the same. Yes? So it doesn't matter if I choose the point here. So if I choose a point n here and I connect it to A and B, the distance in A and the distance in B are equal. And it doesn't matter where do I choose this point. Of course, if I choose the exact M, that is completely trivial by the definition of the midpoint. But any other point has also that property. For example, if I take this one and connect it to here and here, this P, this one is equal to that one, this one is equal to that one. If I go a little bit further, for example, here, I don't know, let me take it P prime, and I connect it here and here, and this line and that line are the same. That's important. It's a very simple fact, but I think you need to remember that. So why is that true? So let us now prove it. So I have this midpoint M, meaning that this line segment is equal to that, and then I have A and B. So let me choose any random point on this perpendicular bisector. Let me call it P, and then I want to prove that PA is equal to PB. So why is that? This is very simple, yes, because this angle is 90, this angle is also 90 because of the definition of being perpendicular. And then I know that this side is equal to this side because they are, this point is the midpoint, and you see that PM is in common. Yes? So the left-hand side triangle and the right-hand side triangle are congruent based on SAS congruency rule. Yes? Is that understandable? And if these two are congruent, then what happens? Then AP and PB, they have to be the same. So I know that the triangle APM is congruent to triangle BPM. And this means that, of course, AP and BP are of the same size. Yes, is that clear? So this is a simple but very important fact to remember. Okay, but of course, the other way around is also true, but we haven't studied that yet. The problem is that if you have a line segment, and then you have a point, which of course you don't know if it lies on the perpendicular bisector or not. But you know that if I join P to A and if I join P to B, I know that PA is equal to PB. That's a very important thing to remember. You can always conclude that P is definitely on the perpendicular bisector of AB. I want you to understand that's not the same theorem. Yes, that's the converse of that theorem. Here I knew that P is on the perpendicular bisector. I proved that PA is equal to PB. Here I do not see any perpendicular bisector. I know that the P point, its distance from A and B are the same. I want to conclude that P belongs to the perpendicular bisector. Yes? How do you think we can prove this?
We could say that the triangle is an isosceles triangle, because both sides are equal. And then from there we could say that since if then we can also say that the angles from on A and B on this like triangle that we've drawn would
So we know that
the
these angles are the same. Then what?
And then we could use the same, or then we can say that if we were to draw the midpoint of A and B.
So what you are saying is that, okay, I have given you this line segment, you find the middle point, M, and then?
And then I think if we imagine we connect P and M.
We join this.
Then we can prove that these two triangles are congruent because they have two lines, two lengths in common and an angle.
No, so three of them. Yes.
Yeah, actually.
So because this is equal to that one, actually we can prove it. I thought that it needs something more, and this is equal to that one, and then this is in common.
Yeah.
Now this one, based on SSS congruency theorem, they are congruent, and this means that this angle M1 and this angle, so let me call this M2 and M1, are the same. But on the other hand, the whole angle should be 180, so each one of them is 90. But the logic is completely different. I want you to understand. So you have to write it down in this way. So if I have this, I have a point P. I know that PA is equal to PB. So if you want to write it down, this is my assumption. So I know that this is already equal to that. So you say that I find the midpoint of AB and I call it M, and I join P to M. Okay? In order to show that P lies on the perpendicular bisector, if I succeed to show that PM is actually part of the perpendicular bisector, I am done. For proving that PM is part of the perpendicular bisector, I have to prove two things. One thing, I have to prove that M is in the middle, but I don't need to prove anything. I chose P and M in that way. The other thing, I have to show that this angle is 90 degrees. And this comes from the fact that this one is equal to that one based on what I have given to you. M is, I myself chose it in the middle, so these two parts are the same. And then you see that PM is also in common between these two triangles. Now, based on SSS congruency theorem, these two are congruent, so these two angles are the same, so it means that each one of them is 90 degrees. Okay? So that's an extremely important theorem that I want you to know. If a point is on the perpendicular bisector, the distances from the endpoints are the same. If you have a point that you know the distances from the endpoints are the same, then it lies on the perpendicular bisector. So we can say that, this is by the way, you can say that the perpendicular, let me write it in that way, that is important to know. So the perpendicular bisector of the line segment AB, this is the terminology I want you to learn, is the loci of points in the plane that are equidistant from A and B. Yes, so this terminology I want you to know is very common. So let us play a little bit with this word, because this is very, very common in geometry. So loci, probably I don't know, it's a Latin word, and I think it's coming from the location and thing, and that's a good thing. Because we can say that the perpendicular bisector is the location of all points with that property. Yes? Okay, so let me try to test your intuition a little bit with simple things. So I give you a point on the whiteboard. I'm not working in space, we are working planar geometry. So I give you a point, let me call it O. Yes? And I ask you, what is the loci of point whose distance to O is 5 centimeters? I want you to know the word loci. So if they write a question with the word loci, so you need to know what is the loci of points on the plane whose distance to O is 5 centimeters. Yes?
Is it a circle with radius 5 that centers on?
Yeah, is that clear? So it means that I draw a circle whose center is this O and its radius is 5 centimeters. What does this mean? Let us test. It means that every point, if you want to show that this is the loci, proving something is a loci contains two parts. First, you need to choose a point from your location, proposed location, and show that it has that property. What is that property? If I choose any random point on this circle and I find the distance to O, then definitely it becomes 5 centimeters. Now, forget about the picture. Now, I give you a point which I don't know lies on the loci. I know its distance from here is 5 centimeters. Then this means that this M belongs to that circle. So this you have to prove it in two ways. Yeah, so you have to do both of them. First, you choose a point on the loci that you proposed, and you show that it actually enjoys the geometric property, which is the distance from O to B5. And then another thing is that you choose a point with that property, and you have to show that that belongs to the loci. Yes, this is always the case. For example, so if I draw a line for you, a line goes to infinity. If I ask you, what is the loci of points whose distance to this line is 5 centimeters on the plane? Yes, yes?
Parallel line 5 centimeters away.
Not exactly.
Two
parallel lines. Yes? So, because one parallel line with 5 centimeters go here. By the way, you know that the distance between two parallel lines is the distance between is the perpendicular line. So this is 5 centimeters, and then I have another 5 centimeters here. So these black lines that you see here are the loci of points on the whiteboard plane whose distance to the blue line is 5 centimeters. What does it mean? It means that if you choose any point on the proposed loci, it enjoys the geometrical property that you mentioned, meaning the distance from that to this blue line should be 5. On the other hand, if you clean these two lines and just imagine a point whose distance to the blue line is 5, then that point should definitely lie on this loci. Yes, is that clear? Now, can you solve the same problem if I work in space? what is the loci of points whose distance to this blue line is 5, but I'm allowed to use points in a space as well this time? Yes?
So you're talking about 3D space.
Pardon?
So you're talking about 3D space.
Yes.
Yeah, it would be a cylinder who.
Yeah, it would be a cylinder, yes?
On the
So
side.
if this is 5, that would be a cylinder around that. Every point on that surface of the cylinder distance would be 5 from that one. Yes, you have to imagine. Is that clear? So this is the word, they use a word loci, which is very, very common in geometry. And I want you to know that. Okay. Now, this will bring us a very, very important concept. And that is the concept of circumcenter. Okay? So what does it mean? If I have a triangle, let me just write it here. I have a triangle here. I think I did it for some of you, I think, in the lesson. So the point was, can you draw a circle that passes through these 3 points? So it is a bit of challenge if you even have your compass here with you. It's not that easy to draw a circle that passes through these 3 points simultaneously. Because, for example, you can manage actually to draw a circle that passes through these 2. It's not that hard. But that's also a bit of challenge. By the way, let us just think about it. First of all, can you tell me how can I draw a perpendicular bisector with a line segment? Just the ancient tools, yes? A straight edge, by the way, that is the word they use for the ruler, which is not calibrated. Straight edge and compass, yes? So if I give you a line segment, how can I draw a perpendicular bisector for this? Yes?
If you draw a circle centered on B that passes through A, and a circle centered on A that passes through B,
Yes.
and then the intersection points of those. And you
Yeah,
draw a
that
line
will
between-
work.
Yeah.
Yes. So let us just see that. So what you are saying is that you put the needle of the compass here and open it this far, and then you draw a circle. I will not draw a whole circle because it would be hard. That would be that part. And then you, without changing it, so you put the needle of the compass here this time, and then open it the same thing, and then you do it here. Yes? Oops. And then you are claiming that if I connect, of course this picture is very ill, but if I connect these 2 points, you have to prove this construction method works. Yes? So you have to prove 2 things. You have to prove that this intersection point is indeed in the middle, and you need to show that these 2 angles are 90 degrees. Yes? So this is the construction method that you proposed, but you have to defend why this method works. That's always in the content of the problem itself. So why it works?
If you give one of the
So
intersection points the name,
M,
yeah, and then you connect A to M and B to M.
yes?
Okay, I don't.
Then it will be the same distance because one
Well,
of these lines.
Now what can I say about MA and MB? Are they of the same length or not?
Yeah, because they were both made from circles.
Yeah, because
with the same radius or the
because
line
of my
there.
construction method, yes? So MA is the radius of this circle.
No,
MB is the radius of that circle. So this, and in the way that I constructed that, these 2 circles have the same radii. So this is MA is equal to MB is by construction. You can say by construction MA is equal to MB. You really don't need to explain that much. Okay, then what? So this means that M belongs to MA is equal to MB. This means that M belongs to what? To perpendicular bisector. So let me write PB for short. Of AB, yes? Is this understandable? We just showed that. If I have any point on the plane whose distance from the end points are the same, so this means that it belongs to the AB. Okay, then what? But I know that M is a point on PB, but this doesn't guarantee that it's still this is a
do the same
perpendicular.
thing for the
We
other.
can say the same thing exactly for this one. So then you say that NA is equal to NB. This means that N belongs to perpendicular bisector of AB again. And then I am done, yes? Because if I know 2 points of a line, then this line has to be that line. Yes? So you see that I didn't start it from scratch. I just used that for the loci, this being a loci. So that is possible to draw. And by the way, you really don't need to open it like this, but you can open these circles so that it should be a little bit more than half. Yes? That also works. So, but this is probably a very good way to do it. Yes, because when you open it, even if you can open it much bigger. But the point is that there is a threshold. You cannot open it less than half. Because then those two circles will not intersect. So you have to make sure that they intersect. Okay, now let us go back to this problem. The point is a very important theorem I want you to know. I have 3 line segments, so in principle I can talk about 3 perpendicular bisectors. Yes? Of course, if I draw the perpendicular bisector here, for example for AB, of course this will go forever, but let us just concentrate on this part. And then if I just draw the perpendicular bisector of this, so let me call this M, let me call this N, and I draw the perpendicular bisector of that. So they intersect at a point O. Okay, so that is more or less obvious, but I think it's also good to think why they intersect. Okay? But the other part is actually important. So I say that, okay, I drew this one, they intersect at a point. The point is that the third one also passes exactly through O. It is not trivial. It might be the case that when I draw it, it passes a little bit from here. Why this is guaranteed? That if I draw the third one, it will also pass exactly through O. Then we have this theorem. A perpendicular bisectors of a triangle, of any triangle, are, this is the word, concurrent. Concurrent means they pass through one single point. That is the terminology, yes. Perpendicular bisectors of any triangle are concurrent. Okay, why is that? So I just tell you, okay, I draw this one. This is perpendicular bisector. What does it mean? It means that this length and that length are equal. These angles are 90. I know that this line is also perpendicular bisector for BC, so this means that this length and that length are equal, and these are also 90. But we want to show that the third one passes through O as well, which is not trivial. In principle, it need not be the case, yes, but it is. Why is that true? Okay, we can do that like this. So let me ask you something. O, so you can just tell me what can I conclude. O belongs to the perpendicular bisector of AB. Okay, from this sentence, what can I conclude? The main property of the perpendicular bisector is what? If a point is on the perpendicular bisector of a line segment, I can conclude the distance from that point to the end points are the same. Yes, so I can conclude that OA is equal to OB. Yes, agree? So this means that OA is equal to OB. Yes. And then, on the other hand, O also belongs to what? Belongs to the perpendicular bisector of which one? BC. What can I conclude from here, everyone? What can I conclude? OB is equal to OC. So this means that OB and OC are the same. Okay, and then what can I conclude from this? Is it trivial? OA is equal to OB. OB itself is equal to OC. So what can I conclude? I can conclude that OA is equal to OC. Agree? But now, what can I conclude from this one? I have a point. I still don't know if it belongs to the perpendicular bisector or not. But I realize the distance from O to A and the distance from O to C are the same. So it means that this point lies on the perpendicular bisector of AC. Yes, this means that O belongs to the perpendicular bisector of AC. In other words, the perpendicular bisector of AC passes through O. Yes or no? Is that understandable? So you see, it was very, very simple. I'm just using the property, the main property of being a perpendicular bisector.
And that's also how you draw a circle that passes through.
Yes, now the construction problem is solved, yes? So what you need to do, according to this problem that you described, in principle using a compass and a straight edge, I can draw this perpendicular bisector, I can draw this perpendicular bisector, they will intersect at a point, then I put the needle of the compass here and open it with one of them, because these three red lines are all equal now. And then I just need to concentrate with one of them. So when I do that and I start drawing the circle, because these lines are all the same, so this circle will also pass through P and P seen automatically. Yes? And that there is a name I want to describe. This point O, this is common, we show it with O. I mean that if you just open a geometry book and then they talk about O without explaining, they mean this, and that is called circumcenter. Okay? Circumcenter. That is called circumcenter, and this circle is, I cannot draw it perfectly here, that is called circle. And the radius is called circumradius. And this is reserved to be denoted by R. This is reserved, the O is reserved for this. Usually this is the case, we denote this by capital R. With little r, I mean something else. We will talk about that. So these are the terminologies I want you to know this, and that's a very, very important theorem. And by the way, let me ask you one question now.
Wait, so the O is the circumcenter
Center,
and R is the circumradius.
radius.
Okay.
Yeah. These are the terminologies for
Okay.
this. Now the question is, one question is still not trivial. Do you think so? I introduce you a method of drawing that circle. Do you think this is a unique way? Is this circle unique, or might be someone else can find another circle with another center that passes through these 3 points? Is it possible?
Another circle that passes through.
Yeah.
I don't think so. I was just thinking about that.
No, but can you defend? So yeah, it is clear that there are no other ones. But is that clear? Why?
Like, or It
Yes,
feels super clear, but
yeah, super clear.
I
But
cannot. Why is that super clear?
Is it because there's no other point that has the same distance from A, B, and C, except for O?
yes, so it means that if you have in principle that if you want to have another circle that passes through these these three, and O is somewhere else, then the distance of that point from these should be the same, but then it should lie on all the perpendicular bisectors, and that's exactly all. Yes, okay. So this is a very, very simple fact, but very important. I want you to know about it. Okay, now we go to another topic of congruency, and that is a theorem that is called theorem. This time I want to write angle, side angle, congruency theorem, congruency rule. So do you remember, so far we had side, so that if you want to count in order, that was an axiom, and then we were able to prove SSS congruency rule from SAS axiom. But now we want to talk about this one today, which is also a very important rule. It means that if I have two triangles, for example this one, I have to be very precise. I should be able to draw, but this is not possible, of course. You need to imagine that they are exactly the same size, okay? A prime, B prime, C prime. So in this, I give you that angle B is equal to angle B prime, for example. I also give you that angle C is equal to angle C prime. And I also tell you that the side included by these two angles, which is BC from the left one, is equal to the side included with these two angles, B prime, C prime. My claim is that we want to prove that ABC is congruent to A prime, B prime, C prime. Yes? And this is called two angles and the side between them. So this is why I intentionally wrote S in the middle of the angle. So this is angle side angle theorem. If I can prove this, then it means that from now on I have something else in my hand. If I have the equality of two angles and the side included by angles from one triangle matching with the corresponding elements of the other triangle, then I can conclude that these two triangles are actually congruent. Okay? Why do you think this is the case? This is now a theorem. This is not an axiom. We should be able to prove that. So, if you don't mind, let me just speed up a little bit, and then you can help me to fill in the blanks sometimes. So, I would say that if AB is equal to A prime, B prime, we are done. Why? But of course, in the exam, you shouldn't write "we are done." You should explain. But why we are done?
It's just side angle side.
It becomes side angle side, yes? So if I want to prove that these two triangles are congruent, if you also tell me that AB is equal to, as I don't want to put it, if AB is also equal to A prime, B prime, I can just forget about angle C. Then I will have BC is equal to B prime, C prime, and this angle is equal to this one, and then that one is also equal to this one. And then it becomes side angle side, and they are congruent and we are done. Okay? So, If this is the case, we are done. So now, what happens if this is not the case? So let AB be not equal to A prime B prime. Yes? Let us see what happens there. Okay, if AB is not equal to A prime B prime, then I will have two scenarios. Yes? Either A prime B prime is larger than AB, or A prime B prime is smaller than AB. These are two options, yes? Or. So let me consider number one and this number two. So let us just think about this scenario. This scenario is very, very similar, and you can just do the argument exactly the same. So, for example, assume that A prime B prime is greater than AB. Okay? So then what happens? If A prime B prime is greater than AB, then somewhere here I can find a point. Yeah, this is not possible, so you need to imagine it in your head, just purely logic. Yes. If A prime B prime is larger than AB, then somewhere on this point, somewhere on this line segment, I can choose A double prime in a way that this part, yes, becomes equal to this part. Is that understandable? Yes? Okay. So you need to explain. I explain these things orally. I don't want to write them down, but you have to write them down properly. Okay? Is that understandable? And now what I do, I join A double prime to C prime. Okay? So what I know, let me write here. By the method of construction, I know that A double prime B prime is equal to AB. This is, we know. Okay, now this original triangle with the new triangle that I constructed, they become congruent. Yes? But why? Because I myself chose A double prime B prime equal to AB, BC is also equal to B prime C prime, and this angle B from the beginning was equal to this angle B prime. So this means that I will have this one. I will have B equals to A double prime B prime. I know that angle B is equal to angle B prime. I know that side BC is equal to B prime C prime. So based on SAS congruency rule, I can conclude that ABC is congruent to A double prime B prime and C prime. But that is contradiction, yes? Why is that contradiction? Because when they are the same, this tells me that angle C will be equal to which angle? Will be equal to this angle. Yes? If these two triangles are congruent, this angle should be equal to this angle. Yes? So this means that this angle C is equal to angle A double prime, C prime, B prime. Do you agree with that one? This is the immediate consequence of this congruency. But that is contradiction. Why?
Because it's supposed to be equal to C prime.
Yes, but that's also just so. On the other hand, we knew that these two angles are the same. So this means that because C is equal to C prime, this means that angle A double prime C prime B prime, which is equal to C and C itself is equal to C prime, should be equal to C prime. But this is not possible, yes, because A double prime C prime B prime is just one part of angle C prime and it cannot be equal to C prime. Is that understandable? So in principle, if you agree with this one, you have to admit that this angle is equal to this angle. Yes? On the other hand, put it in another word, it means that this angle should be 0. But if this angle is 0, it means A double prime is exactly on A prime. This is also another way to phrase it. Yes? So that is also a very, very important rule that we added here. So we add to our list here ASA. Okay?
We don't have to prove it on the other scenario.
You have to prove it in principle, but you can say similar. I hope that you agree the argument is similar.
Yes.
So instead of finding a double prime on the right hand side, you try double prime on the left hand side triangle, and then you can do the same thing. But you need to explain them properly. If I want to write these things, we are just wasting our time, I think, because that is not hard to understand. Yes? Okay, now I want asking you a question. These are very common, even you have it in the Swedish system. But what do you think about angle side? Yes? So do you remember, when I was teaching you SAS, I also talked about this scenario, SSA. Was it right or wrong? So this tells you that a side, two sides and one angle, not necessarily between them, from one triangle is equal to the other one. Can I conclude that the triangles are congruent? No. The answer to that was no. If you go and review the video, so we just realized that if I have two sides and one angle, this is important to have that angle being between the sides. If this is just two sides from one triangle and one angle from another, two sides and one angle, this is not necessarily the case that the triangles are congruent. Yes? Do you remember that or not?
Yes.
Yeah.
Yes? So for SAS, if you want to use it, it is extremely important if you have two sides. The angle that you have is exactly the angle between the sides. So you cannot have this with that angle.
Oh, yeah.
This is not working in the case of two sides and angle. But now my question is that, can I have two angles and side, regardless of if that side is between those angles or not?
I don't think we can say that we're congruent.
No, I do think we can. Can't we?
Yes or no?
I say no, but...
If you say no, you need to convince me by a counterexample, and if you say yes, you have to convince me by a proof.
Yes.
Like...
So is the question clear? Let me draw some picture for you. For the case AAS. So for example, for the case, let me just probably explain if you have forgotten. SSA, I want to show that this does not necessarily work. Do you remember which picture I drew? You can help me as well. So if I remember, I made an isosceles triangle here. Yes. So this one is equal to that one. And then what I do, I just draw this line here. Yes. And then let me concentrate on these two triangles. You can help me, yes? Which triangles we talked about? A, B, C, D. Yes? So, in my construction, I made this one equal to that one. Yes?
Oh, yeah,
And then, let me tell you here. Concentrate on this bigger triangle. I have AB as my side. I have angle B as my angle. Yes? And I have AC, AD as another side. Yes? Consider this bigger triangle. One of the angles is B. One of the sides is A. Yes? And another side is AD. Do you agree? Now, AB, now concentrate on this triangle here. Concentrate on this triangle. AB is also equal to AB because AB is not only the side of the bigger one, it's also a side for the smaller one. So I can write AB from the bigger triangle is equal to AB from the smaller triangle. And then angle B is also the same. angle B is not only an angle for the bigger one, but also an angle for the smaller one. So I can say that angle B is equal to angle B.
Wait, what? Wait.
And then by construction, I made AD equals to AC. I myself did it like that. And then you see that I have side and this angle. Yes? So this is just an angle, not necessarily the angle between them. So now can you conclude that the bigger triangle is congruent to the smaller triangle? Apparently not. Yeah. So this is SSA, and this doesn't work. Yes, this is not working because you can immediately see that the bigger triangle is not congruent to this smaller triangle, even though I have two sides and one angle. You see, it is important that the angle that you have should be the angle included by the sides. So what are the angles included by the sides? So AB and AD, AB and AD, the angle included by that is this angle. But between AB and AC, this is AB and AC, this is this angle. And they are not equal. So you see, it is important not just two sides and one angle is enough. The order in which we have these angles are also important. So the sides, the angle should be included by the sides. Otherwise you will have this mess, which is not correct. But now my question is something similar to this scenario, which was completely wrong, for having angle side. Do you think the answer to this is yes or no? No, you need to draw a picture like this to convince me that this is not the case. If you say yes, you have to have a proof for that. So Oscar?
I want to say yes. And
Yes?
I also updated my answer to yes.
Yeah, the answer is yes in this case. Why? Because, for example, consider this triangle ABC and this triangle. I want to have an exact copy of that or whatever. So A prime, B prime, C prime. Now, what I'm saying is that assume that I give you two angles. Okay, so for example, I tell you that B is equal to B prime. I tell you that C is equal to C prime. If I give you BC is equal to B prime C prime, that becomes ASA. But now instead of giving you BC is equal to B prime C prime, I give you that AC is equal to A prime C prime. So you see, this is not the previous scenario, yes? The previous scenario was two angles here and the side between them. I have given you two angles, but the side that I have given to you is not between them, it's somewhat. But I am asking you, can I still conclude that they are congruent?
Yes.
Yes, why?
See, I don't, because this is like my answer to this is too intuitive, I feel like. But I mean, it's like...
No, it's very simple to say. So just say it. If it's very intuitive, I can correct you. But how do you feel that this is correct?
I mean, the way I thought about it was like, if you want to change the side if you say that there's a difference between the sides, you have to admit that there's a difference between at least one of those angles.
Okay, so I think you are starting from scratch again.
Yeah.
I want you not to do this. Okay, I want you to learn to construct a new concept on top of exactly or previously constructed idea. It's much simpler, yes. You can reduce this problem to this problem, that's done. Finished, yes, because if I give you this one is equal to this, and I give you this one is equal to this, it is completely clear you can conclude that this angle has to be equal to which angle? Because the sum of the three angles should be 180 degrees. If this one is equal to this one is equal to this one, it is inevitable. These two has to be the same.
Don't we?
Yes? And now don't look here. What do you have? You have two angles and the side between. This is the correct way to look at the problem.
Oh, yeah,
of course, you might be able to do something similar to this one as well.
Yeah.
But I would call it starting from scratch over again.
Okay, so like if we did... Oh yeah, and just having three angles is not enough.
No, it's not enough.
No,
Oh,
so
no.
that's why we haven't been able to use this fact yet.
Yeah.
Okay.
Well, okay, yeah, angle.
Do you understand? The reason is very simple.
Yeah.
I just reduced a new problem to a previously solved problem. Is that clear?
Yeah.
So from now on, you can also use AAS. Okay? So, but AAS has a nice consequence. I want you to memorize it, or I want you to know it, about right angle triangles. Okay, so for particular triangles, we can have more than these. For example, if I give you two equilateral triangles, and I just give you equality of one sides, can you conclude that they are congruent?
They're equilateral.
Yeah.
Wait, what was it? Equilateral now again.
Equilateral means all sides are the same.
Okay.
Yes? If I give you two equilateral triangles, instead of giving you SSS, I just give you S. Is that enough here, in this particular
Yeah,
case?
yeah.
Yes, because if one side is equal, then all the sides are equal. So this problem reduces to SSS theorem.
Oh.
Yes?
Wait, how would we define equilateral triangles? Have we defined it by the angles being the same or the sides being
The sides to be the same.
Okay.
But the angles
of
being the
course,
same is a consequence of the sides
Yeah.
being the same. Yes? Okay, and then another question, for example. If I want to give you a right angle triangle, so what can we add to this scenario? Of course, not adding, but the way you think is important. So I give you a triangle. So I try to make them congruent. So this angle is 90. And then I will draw another, try to copy paste more or less the same picture. Okay, so let us, of course, we haven't talked about Pythagoras Theorem in a systematic way in this lesson, we will. But for the time being, okay, if I give you this side is equal to that side, and this side is equal to this side only, can I conclude that these two triangles are congruent?
Yes.
Yes, because automatically this angle is 90, so that becomes SAS congruency rule. Yes? Or if you knew the Pythagoras theorem, you can reduce this problem to SSS. How? Because if this one is equal to this one, and this one is equal to this one, and if we assume Pythagoras theorem is known to us right now, we can conclude that the hypotenuse is also equal, so then I can conclude that this is SSS. That's one way. But now my question is that, can I conclude this? I give you this hypotenuse is equal to this hypotenuse, and one acute angle is equal to one acute angle. That's it.
Yeah.
Can I conclude that these two triangles are congruent?
There's angle side.
Angle side. So remember this extra piece of information somewhere in your head. If an acute angle and a hypotenuse of one right angle triangle correspondingly match with these things from another right angle triangle, then they are congruent. That's extremely useful.
But do we need that acute angle? Can't you just, isn't this, like if this is a right angle triangle and the hypotenuse are the same, shouldn't it? Well, I mean, I guess that's
No.
Pythagorean theorem. I guess.
No.
No?
No. What I'm saying is that. So you mean that even if I don't give you, that's enough?
Isn't it?
No.
Am I right?
No, we can have completely different. For example, I can have this scenario.
If you make one side
A very,
smaller
very narrow-
and longer, then you should like slide it around.
This one. Yes. The hypotenuse of this narrow triangle is this one. The hypotenuse of this bigger triangle is also this one.
Oh, okay.
They are not congruent, yes. So that is needed.
Yeah.
So if this is remember hypotenuse, one acute angle. That's enough. Okay. Okay. Let me ask you another question. Hypotenuse and one side, is it also enough? According to Pythagoras theorem, you already know the answer.
Yes, that would, yes.
Yes, because if, remember this, if I give you the hypotenuse is equal to this one side is also equal to this one, and if we assume that we know Pythagoras theorem, then we can immediately conclude that the third side is also equal, then it becomes side. So these two extra pieces of information I want you to remember regarding congruency of the right angle triangles.
So
Yes.
are we going to prove Pythagoras theorem.
No, not yet. So the first one was not using Pythagoras Theorem.
No.
Yes?
But
It
are
was
we-
AAS.
Are we going to do that in this lesson?
Yes, we will do it, yes. Yeah, I will at least systematically try to talk about that. Okay, so now let me see what else is left. Okay, this is also a very simple fact, but I want you to know, and that is the idea of the angle bisector. So do you remember what was the perpendicular bisector when I expressed it in the terms of loci? I said that perpendicular bisector of a line segment is the loci of points which are equidistant from the endpoints.
Yeah.
Now, can you just give me a sentence giving something like this for an angle bisector?
It's the loci of the points that are equidistant between the two.
Okay, but do you exactly know what? Because what you express is completely correct.
I mean,
But what is the
they're-
meaning of
they're
equidistant
the same distance.
from the sides?
they're the same
This is
distance.
not that trivial as before. Yes. So, but what you said is completely correct. Okay, thank you. So, what you want to talk about? So, what we want to talk about is this. If I give you an angle, extremely simple but very, very handy. If I give you an angle, so let me say angle O, and if I draw the the angle bisector, meaning that I draw a ray, which actually divides this angle to exactly equal pieces, to two equal pieces. And then what you said, if I understood you correctly, you told me that this angle bisector is the loci of points that are equidistant from the sides. But this needs explanation, because if I give you what is the distance from the point A to point B, then it means that you put your straight edge here and draw this, and then if you have a measuring tool, you measure this length, and that will be the distance from A to B. Yes? But if I have one point, and if I have a line instead, and I give you a measuring tool, and I ask you measure the distance from this point A to line L, then you have to have a definition for that. Because do you consider this the distance? Do you consider this the distance? What do you consider? Yes?
You just consider
Because
the perpendicular
Yes.
line that intersects with A.
So yes, so you draw a perpendicular line, exactly what we discussed last time.
Where
And then you draw this line, whatever they intersect, you measure with your measuring tool this
Or
distance.
in other words,
This should be 90 degrees.
or in other words, the smallest possible distance between.
Not other words, but you need to defend that. Why, if you do this, that's the smallest distance. That's right.
Yeah.
But we have to show that. We still don't know.
If we
So you are claiming that. First of all, let me don't confuse you. If I give you to measure the distance, you need to draw a perpendicular line from that point to your line, and then when you find the intersection point, find this distance. By definition, this distance is the distance of A to L. That's the definition of a distance from a point to a line. But now we are claiming it's a good definition. This is the shortest possible distance from A to any other point here. Why?
cannot use Pythagoras Theorem.
Not yet.
Yeah, because
I want you to refresh your memory about what we had before. So let us do this claim here on the board. We had this theorem. I want you to refresh your memory every now and then. So if I give you this line, and if I give you this point, and I ask you what is the distance, according to this definition, I draw a perpendicular line. By the way, is this unique or not? Because if that's not unique, I am in trouble.
What's not unique?
Because you know, if you can draw many different perpendicular lines, then there are many different distances. But is it possible to draw more than one perpendicular line from A to this line L? No. Intuitively, no, but reasoning, why?
Because...
So I'm asking you, for example, is it possible someone else draw another line which is also perpendicular? Of course, it is not happening, but you need to imagine.
If we imagine, I think we can use our axiom of like parallel lines.
Yes?
If we just imagine that we could draw a perpendicular line anywhere on L, that just anywhere doesn't matter, then we, by that axiom, we know that there's only one line who is parallel to this line that also passes through A.
That is parallel axiom.
Yeah.
Yes.
And could we use that?
But of course, no, they are not parallel because I'm drawing them from the same point.
That's why we, like, before drew
No, make it very simple. Why this cannot happen? If they are really different, then I will have a triangle.
Mm-hmm.
And if this angle is 90, this angle should be also 90.
Mm-hmm.
Yes? But this cannot happen because this also is 90.
Mm-hmm.
And if these two are 90, this should be 0.
Yeah, well,
So that should be the same.
Yeah. They have to be the same.
Yeah.
So this is, first of all, you have to convince yourself that this is possible, and that is possible in a unique way. Otherwise, the notion of distance doesn't make sense, because depending on which one people draw, they will have different distances. But why this is the shortest one? What is the meaning of being shortest? It means that if I choose any point here, and if I connect this to this one, if this is M and this is H, you want to show me that AH is definitely smaller than AM. Why is that? It's actually a right angle triangle.
mm-hmm.
So this AM is the hypotenuse, and AH is one side. Of course, if you know the Pythagoras Theorem, it is very simple, yes? Because the hypotenuse squared is the sum of squares of these two. So it is greater than each one of them. But now we don't know, for example, we can pretend we don't know Pythagoras Theorem. So why is that true then?
Triangle.
No, that was another important theorem. The theorem was that if I have a triangle and one angle is larger than the other one, you remember? Then the side opposite to this is longer than the side opposite to this.
Yeah.
This was a theorem. Do you remember? We talked about that. The converse of this one also was true.
Yeah.
Yes? And this is so you know that this angle is definitely larger than this angle.
Yes.
This is an acute angle. The sum of these two should be 90. So each one of them is smaller than one. So the side opposite to this is shorter than the side opposite to this. Yes? Of course, Pythagoras Theorem is probably easier for you in maths, because that's more famous than this theorem.
Is that hard to prove?
Pardon?
The Pythagorean theorem? Is that?
No. Yeah, we can. I think it's very simple, not hard. Okay, so now we are convinced that what is the meaning. Now, what you are saying is that if I choose a point on the angle bisector, the distance from this point to this arm, meaning what? Meaning that if I draw a perpendicular line here, this is equal to if I do the same thing here. So we want to show that these two are the same. Yes? So why is that true? So is that understandable? So what you said, it's not finished by the way. What you said is that the angle bisector of an angle is the loci of points on the plane of the angle whose distance from the arms are the same. But here the distance from the arms means perpendicular lines. Yes? Why is that true? It's very simple. Because this angle, if I call it alpha, what can I call this one?
Okay.
Alpha, because that's angle bisector. And this triangle is what? A right angle triangle by the definition of the distance. So what can we say?
It's congruent.
Why? Because the hypotenuses are the same,
Yes.
and I have an acute angle the same. According to that extra piece of information that I told you, remember for the right angle triangle separately, these two triangles are congruent. If these two triangles are congruent, I can immediately conclude that these two line segments are of the same size. But is it finished? To say that's the loci. You remember every loci it consists of two problems. One problem, you have to choose a point on the proposed loci and show that it enjoys the geometric property that you want. So here we did it. So I took a point here, I draw the perpendicular line here and there, and I could prove that these two lines have the same sizes. But this problem is not finished yet because of the word loci. What should I do to finish the problem? What should I
Prove that no other.
Yeah, this doesn't work anywhere else.
Yes, it doesn't work anywhere else. Or in other words, if I have an angle and somewhere in the interior of that angle I have a point which I know is equidistant from the arms. So I know that MH is equal to MH prime. This is my assumption now. I want to show that M belongs to the angle bisector. To the angle bisector for short. So if you don't do this, it is not finished yet. So whenever you see a problem having the word loci in it, you have to solve two problems. Yes, you need to choose one point on the loci and show that it enjoys the given property in the problem. And this time you just choose a point which enjoys the property, and then you have to show that it lies on the proposed loci. Okay, so how should I prove that this? If this length is equal to this length, how can you convince yourself that M lies on the perpendicular on the angle bisector?
If you connect.
Oh, yeah, we
Yes, it seems to be a good idea just to connect, join. Because I cannot say that I join and it is, no, that's not possible. I just join this to this. Okay, then what? So here we know that this length is equal to this length by this assumption. Okay, then what?
we have two equal sides.
No, this is side-side angle, so it's not.
Yeah, but wasn't that didn't that work for no wait. Yes, that worked for
No, we don't know yet. It's not under our control, yes? I'm just drawing the perpendicular line from here to here. I don't know if these distances happen to be this. Of course, they are the same, but we don't know yet. But what you said is correct.
Yeah, wasn't that a special case with
right angle triangles,
triangles,
yes? Because what do we know?
Yes,
This is a right angle triangle, this is a right angle triangle by the definition of the distance. And then I have this side equal to that side, yes? But I also know that the hypotenuses of these two triangles are the same. So it becomes that another special case for right angle triangles. If hypotenuse and one side are equal, then the third side has to be equal, of course, by Pythagoras Theorem right now. Yes? But the question is that, is there any way to prove this without Pythagoras Theorem?
Can we use the fact that all the angles added together is 180 degrees?
Okay, but this will not help. Because we don't know these angles are the same now.
Can we use side angle?
Side,
And then 90 degrees.
and 90 degrees. Do we have side angle?
That
No.
was the one that didn't work.
The one that I excluded. It was not working. That's exactly the same scenario. So I have seen students write these things, but be careful because they say that, okay, I know that two sides from this are equal to the two sides of this one, and I know that one angle is equal to that angle, so then we can conclude that these two are the same. Yes? But I was reading a book yesterday, It was written by Amol Sasane, and I chose some of them from that book. It's very nice. I haven't seen that theorem before. There is something for SSA. So if you have SSA, you cannot conclude that they are congruent, but there are two cases. Either they are congruent or two other angles add up to 180. Okay, so we should be able to prove this. So, first of all, let me conclude everything here. So, the only thing we don't know yet is why, in this case, two sides and two sides work for the right angle triangle. But of course, Pythagoras Theorem is so famous that you realize that if this one and this one are equal with this one, and because this is a right angle triangle, the third one should automatically be the same. So this proof is complete. So from now on, add this one also to your list of congruency theorems for the right angle triangle, yes? Not for the others. But then I really want you to memorize that theorem, right angle bisector. If someone asks you what is the angle bisector, you would say angle bisector is the loci of points interior to the angle whose distance from the arms of the angle are the same. Yes? So this is important to know, extremely important. Okay, and now I want to give you this as an exercise for yourself. So what I am telling you is this. We want to talk a little bit about SSA, which I told you this is not correct in general. And I just drew a picture, if you remember here, to convince you this is not the case. But I want to tell you this. If, for example, in a triangle like ABC, and then let me just draw another one, A prime, B prime, C prime. If side AB is equal to side A prime, B prime, and side BC is equal to B prime, C, so side AC be equal to A prime, C prime. So this one is equal to that one, and this one is equal to this one. If I give you B is equal to B prime, of course I can conclude that these two triangles are equal because that becomes SAS. But now, what happens if instead of giving you this, I give you this one is equal to that one? So let me see. Now I want to make sure.
You wrote that AC is equal to.
No, yes. So let me write A be equal to that one.
Yeah, but you wrote that AB and is equal to AB prime, and that AC is equal to AC prime. So.
Okay. Yes.
It would be BC equals to
Okay,
BC
so it
prime.
cannot be. Yes, you are right. I have written that AB is equal to A prime B prime. AB is equal to A prime B prime, and then I have written that AC is equal to A prime C prime, but I want to choose another angle. Yes. B is equal to B prime. Yes, you are right. So B is equal to B prime.
Yeah.
So I know that this angle.
Then you should
No,
write.
this I have to remove this. I'm just confused myself because of that. Yes, I know that AB is equal to A prime B prime. I know that AC is equal to A prime C prime. Instead of giving you the equality of these two angles, which immediately give me the congruency of these two triangles using SAS, congruency rule, I give you that angle B is equal to angle B prime. Okay? This is what I call SSA. Then SSA tells you that either, this I want you to solve for the next time, either the triangles are congruent or this angle is plus this angle is 180.
I would see even working. Yeah, I mean, that triangle would be very, very weird. Because then C would have to, then C would have to be on like the left side of, then C prime would have to be on the left side of B prime. So then.
No. I mean, the picture that I have drawn is more or less reminding you of this scenario.
Yeah.
But
in the other
that's a part of the
in
problem.
case 2.
So one of them might be bigger, one of them might be narrower.
Exactly.
Yes, that's exactly what I'm trying to say. So if you want to imagine the other scenario, you have to imagine something like this. Yes. So here, this is equal to that one. Of course, this is not a very bad picture. I want to keep this one equal to this one. And then you see that in this case, this angle and that angle becomes 100, the sum becomes 180 degrees.
But like in that, I mean, because actually, wait, hold on. Because what I'm thinking is that, like, if you had because we had the other example where it was like, we had this triangle and the angles.
Exactly.
But if you had this triangle and you wanted to prove that, like, this.
Yeah, in that example, if you remember, that was 180 degrees.
But then that side would have to. It went like this, but I have to go to the other side. So
yeah, no worries.
Yeah, I mean, but they.
No, because the bad thing is that let me clean the pictures. This is a bad way of expressing. Might be I was confused myself. So I was saying I want just pure logic. I am giving you 2 triangles. I'm not drawing any shapes. I give you one triangle ABC, and I give you another triangle A prime, B prime, C prime. That is possible, yes? And then I tell you that AB from this triangle is equal to A prime, B prime from that triangle. I say that AC from this triangle is equal to A prime, C prime from that triangle. And I also tell you that angle B is equal to angle B prime. I give you just these pieces of information without drawing any pictures.
Yes.
And then I am telling you that what is this we call SSA. And then I want to tell you that either we can conclude that these 2 triangles are congruent, or there is another possibility, and that is the case that angle C plus angle C prime is equal to 180 degrees.
Yes.
And this I want you to prove. Either this happens or that happens. So this I will not put it as a theorem here, but it is good to solve this using whatever you have. This is a problem. I want you to solve this problem to prove it. But if, assume now for the time being, assume that you have already proven that. Assume that this is next week and you know how to prove this. Okay? Which can be done using the information so far without using Pythagoras Theorem. Okay? And now I ask you, if you already have proven this, can you now prove this is possible? If I have side and hypotenuse from one equal to the other one, can I prove this is the case? If I give you 2 triangles like this, so let me write AB, and then I tell you here A prime, B prime, and then I say AC, A prime, C prime, yes? I tell you that this one is equal to that, I tell you this one is equal to that, I tell you this one is equal to that.
Is this or an exclusive or an?
No, usually in mathematics that is always or is inclusive unless it cannot happen.
Okay, because wouldn't.
So you see, this is the same problem. AB is equal to A prime, B prime, AC is A prime, C prime, B is B. There are 2 scenarios going on. Either they are congruent, so then I am happy, or I have to admit, if of course you have already proven this, that C and C prime are supplementary, meaning that they add to 180. But in this scenario, you can easily rule this out. Yes, because C and C prime are acute angles. So they are less than 90.
Yeah.
So when I add them, it becomes less than 180.
Yeah.
So for this particular case, the second scenario should be ruled out. So there is only one scenario left, and that is the first one.
Can I give a proof?
I want everyone to think about, but it's not hard, by the way. That's not very hard.
But I just wanted to show, because I think that this would it would look weird if it was if because in this case the AC was longer than AB. So then if you did the same thing, and it would be, if you drew like a, so it
No,
became an
that is
isosceles.
not necessarily longer. If you draw it with
No,
compass,
exactly.
it is not
But
hard.
if it is, then it would like the interior angle would look fixed.
Are they?
Like the interior angle would it would be like flipped to the other side, so it would look like an exit. Like it would be more than 90 degrees. It would be more. It would be on.
No,
the
I don't
outside.
understand your question. So
Okay,
might be
well,
you are concerned with
hold on,
drawing
I
the
just-
pictures.
Yeah.
I mean that if you want to satisfy these three conditions, you have two different pictures, of course.
Yeah.
One picture are the same, they are completely congruent. One picture you can draw satisfying all these conditions, but if you want to do that, the other scenario is that you have to draw them supplementary.
Yeah, I know.
Yes?
Yeah. I just need to check.
I don't know, is the idea
Yeah,
clear?
it's clear. It's clear.
So I want you to prove this, but I hope that you understand that if I prove this, then I also know this congruency rule for the right angle triangles without using Pythagoras theorem.
So
Yes?
SSA always works for right angle triangles.
Yes. And that's exactly the same thing. That is what I want you to add extra. But if you bring Pythagoras theorem, it is very trivial, because if this one is equal to that one and this one is the same, based on Pythagoras theorem, the third side, as Sarah mentioned, they have to be the same. And then it becomes three sides. It's really important to know these extra things, especially when you're solving problems. We have a little bit of time. If you don't mind, let me introduce you the next concept. So why do you think, if I go to a triangle, I have three angle bisectors, agree? I have three angle bisectors. I want to show that angle bisectors are also concurrent. So why is that? So you draw a triangle here, any triangle that you want, yes? And then I have ABC, I draw the angle bisector of this one. By the way, angle bisector is not a line, it's a line segment. So for example, it cuts this one at D. This is angle bisector, so I'm assuming that these two angles are the same. And I draw angle bisector of this one. Yes? And I call it beta and beta. They intersect at a point. By the way, you have to convince yourself they intersect. But then, I want to prove that the third one also passes through, oh sorry, that is wrong. The common name is I. This is not trivial. Why the third one also passes through I? Can you tell me why?
Didn't we prove before, because AI is equal to BI?
No, no.
No, this is.
We haven't proven that. That was for angle bisect, perpendicular bisector. Are you confused with that?
Oh, okay, that's okay.
So the point is that is very, so this, I want you to take some lessons from the way that I proved the concurrency of perpendicular bisectors. Did you remember? I didn't do more or less nothing. I did more or less nothing. You want to show that the third one also passes through I.
Yes.
How should I prove this?
I lies on.
Can you help me? I want to draw something. So okay, so there is no time, so let me finish it. So, I draw a perpendicular line from here to here. So let me call it H1. I draw a perpendicular line from here to here. Let me call it H2. and I draw a
Oh, yeah.
perpendicular
Oh,
line
okay.
from here to here, I will call it H3. Then what?
And now it's
Now it becomes clear.
It
Yes.
should
So
not be the same.
so what we say that I belongs. This means belongs to AD bisector. So let me write angle bisector. So what can I conclude? I can conclude that H1 is equal to H2. Agree? We just showed that if a point is on the angle bisector, its distance from these arms are the same. And I know that I belongs to B, so let me call it BE, angle bisector. What can I conclude? I can conclude that H2 is equal to H3. Yes? And then these are numbers. Algebra tells me that if H1 is H2, H2 is H3, I can conclude that H1 is H3. Yes or no? Okay, then I can conclude that I belongs to the angle bisector of C, because the angle bisector is the loci of that property. So this means that I belongs to the angle bisector of the angle C. Yes, is that understandable? Okay, and there is a name for this. This is called, I is called in center. Okay, and then, okay, later we will learn that if I put the middle of the compass here and open it up to here, it becomes equal to that one, it becomes equal to this one. So if I draw a circle, this circle will be tangent to all sides.
Isn't that, I mean, the radius is the same.
The radius are the same, but it is not clear why they become tangent.
Okay.
Because tangent has a meaning in circles. We will talk about that later, okay? But of course, intuitively it is clear that it becomes tangent, yes? So this is called in center. I don't know, this one. H is called R. So R, we have in radius. In radius. In radius, I denote it by little r. Do you remember I told you that capital R is reserved for circumradius. Little r is reserved for in radius, which is the radius of this circle. And that circle is, of course, is called in circle. This circle that you see here is called in circle. In radius, in center. And I is also reserved for in center. If this is not explained, R is reserved for in radius. O is reserved for circumcenter. Capital R is reserved for circumradius. Okay. I think we progressed quite a lot here. That was good. But I really saw a problem in this book by Amol Sasane. It's extremely beautiful. And I want to share it with you. It's really type of mathematical contest problem. Yes? I want to describe the problem here for you. And it's really worth it if you think about it. Okay? And it is exactly the nature of so that the author is Amol. I hope that I write the name correctly. The book is called Plane Geometry. So I already ordered this through the library, but it's a very, very nice book. And I think I really enjoyed this problem there. I want to describe the problem for you. It's really worth it if you want to think. It's completely according to the spirit of mathematical Olympiad problems. So the point is that let us f be a function, real valued function. I will tell you what is the meaning of the plane, of the points in the plane. So what does it mean? It means that if, for example, assume that the whiteboard is my plane, I pick a point on the plane, say it A. F is a function, I don't know what type of function it is, but I know that if acts on this point gives you a number, a real number. That is the meaning of a function, real valued function. It means that the value of the function that it gives you is a number. Yes? Is that clear?
Hasn't the lesson ended?
Yeah, I will end.
Yeah.
Okay, real valued function of the points in the plane. But then let me tell you something else. This function has this very strange property that if you have a triangle ABC with its in-center, this condition is satisfied.
Tack.
So this function has this property that if A, B, and C are the points making the triangle ABC and I is the in-center of that triangle, this function satisfies this relation. We are supposed to prove that the function is a constant function. Prove that f is a constant function. So I don't want to explain this more than that because that's also part of the problem I want you to understand. So I have a real valued function. What does it mean? Of the points of the plane. So if I give a point to my function, any point, it gives me a... Yes, you're welcome. It gives me a number. Yes? This is the definition. But how? This has some property, interesting property like that. If I choose 3 points, A, B, and C, and then this I is the in-center, then it has this property that the value assigned to I is the average of the values assigned to these 3 points. Yes? We want to prove, based on these two strange assumptions, that this function is a constant function.
What is a constant?
Constant function, it means it doesn't care what do you put in, it always gives you the same number.
Oh, so f will, so anything.
So for example, if f of a is 5, then f of every other point is also 5. We don't know what the value of the constant is, but we want to prove that actually this is always constant. So you see, it's a very, I would consider it an extremely hard problem if you can manage to understand at least what to do. So it means that you have to be proud of yourself. So that's a very nice problem. It took me actually 1 hour to discover how to prove it before looking the solution. And he has provided 2 different solutions. One was more or less the way that I did it. The other one I didn't know about that. So, but is the problem clear?
Yes.
So the problem is clear, but how to think about the problem is a different story. And it is related to geometry, but also functions. So this nature of the problem that you see on the board is very close in spirit to the problems that you might face in the context of Mathematics Olympiad.
Just to be clear, so because it's all the same, does that mean that f of I is the same as f of A and f of B and f of C?
Yeah, exactly.
And then, okay.
So that is exactly. So it means that whatever number you get, so this means that because this is not necessarily the case, this number could be the average of these numbers without all of them being the same. Being all the same is just one scenario, one possible scenario. But we want to show that if this works for all points and the inner in-center of that, then there is only one option left. We have to admit that this function is just a constant. It cannot give different values to different points. Is that clear? I mean, the problem should be clear, but how to think about the problem, I think it's a very, very important problem if you can figure it out, and at least if you can have some strategy to tackle how to tackle the problem, that is also very good. At some point, I think I have to make some videos for myself. I don't know if you want to join also, because there are many problems that I am presenting, but I'm not able to solve that, and that's not good. I don't know, might be, yeah, I need to find a way to do it. Either I can just record some videos for myself here without you being here, and then if you want you can look at the videos for the solutions, because now the number of problems that I'm proposing without solutions are actually increasing quite a lot. Okay, but this is completely different type of problems that you have faced so far. Yes, it's related to geometry and understanding about functions and things like that. Okay, we will discuss about this problem. Yes, thank you.
Thank you.